Welcome everybody. Welcome everybody. Good morning, good evening, good afternoon to everybody. So I would like to welcome you all to the second edition of our B1- analysis in PD from the South. We're going to be having lectures from today until February 4th. So you're all very welcome to participate and attend all the lectures that we're going to have, the short courses, the invited talks. And you can also follow the program on our website. And we're going to be starting today with our first speaker. And it's a great honor for me to introduce you, Serena Dipierro from University of Western Australia. And Serena will be giving the short course from today until 26. And the short course is entitled The Malmheden Theorem and the Geometry of Harmonic Functions. So thank you again, Serena, for accepting the invitation, and welcome to start whenever you want.
So thank you very much, Juliana. So thanks for inviting me to this beautiful event with actually a beautiful title. Like, I think it's a great title, B1-. It really makes sense. And I have to say that I've seen the logo of this conference, of this school, and I like it because it is exactly, I don't know if other people have seen it, but it's exactly B1-, so like just the Southern Hemisphere. And it's incredible because it's the first time that I've realized like how much water, how much ocean there is in the Southern Hemisphere. So it's really Australia here, South America there. So it's really a lot of water there, but I think it was beautiful. And also, so thank you for joining today. Thank you especially to people in Brazil for waking up so early, and people in Australia for staying so late, which is very late in Australia, considering that usually people here wake up very early and go to bed very early. And also thank you to the participants that are in between, the lucky ones that are in between, let's say Brazil and Australia. So for them, it's a good time frame, probably. Yeah, so I will be talking about, in this short course, I will be talking about a topic which is somehow of classical flavor, as you can see in the title, the geometry of harmonic functions, which is something very classical. But on the other hand, I will talk about this Malmheden Theorem, which I think it's not very, very famous. Like, for instance, I mean, I myself discovered the existence of this theorem very recently. And I thought it was a good idea to give a short course about it, also because sometimes when you have to explain things and talk to people about things, you understand them better. So because it's a very new thing to me, I decided it was like a good topic to talk about. So this is basically the bibliography that I will more or less follow. It's in alphabetical order, so we go from probably the first result that I will be talking about is the one by Schwarz, which is just the last one here that we will see after the Malmheden Theorem. And probably it all started with this result of Schwarz on harmonic functions in the plane in dimension 2, which probably somehow inspired Malmheden, which you see comes a bit later, so in 1934, there is this reference written in German, where he proved the theorem that we will be talking about. And then there are other papers where people more or less revisited this and gave different proofs of this result that I will be talking about. Somehow we kind of stumbled into this problem with Enrico Valdinoci, because we were writing a book, which is this one here, on elliptic PDEs from an elementary viewpoint. So we were trying to do things really from scratch. And probably while studying, I don't remember exactly when, but when studying the geometry of harmonic functions and the mean value theorem and things like that, we kind of stumbled into this paper by Malmheden, and we started investigating a bit. So whatever I'm going to say today can be found in this book, which is in archive. So all the proofs that I will somehow, some of them I will sketch, some of them I will give full proof. They are in this book. And then we will see the fractional counterpart of this theorem. And by fractional, I mean the counterpart of Malmheden Theorem in the setting of non-local equations. And I will define what non-local equation means and what kind of operator we'll be dealing with. In this setting, so we proved some kind of fractional Malmheden Theorem together with Enrico and with Giovanni Giacomini, who is a PhD student at the University of Western Australia. Okay, so I said, okay, we kind of stumble into this theorem when studying harmonic functions and specifically the mean value theorem. So let me just recall like the basic notation that I will be using. So for me, omega will be an open subset of Rn. And let's say u is a C2 function in omega. And so I can define the Laplacian of u at a point x in omega as the sum, so we all know this definition, is the sum of second derivatives in the end direction. And of course, I will say that u is harmonic in omega if the Laplacian of ux is equal to 0 for all x in omega. Okay, and then if you're happy with this definition, we probably all know also the mean value theorem that I would like to recall and prove so that we are all on the same page. So the mean value theorem, we know is some kind of characterization of harmonic function. So it goes like this. You have a domain, subdomain of Rn, an open subset of Rn, and I take a function that is in a L1 log of omega. And then I know that these conditions are equivalent and they characterize harmonic functions. So the function is actually C2, and I can write the Laplacian of u equal to 0 pointwise in omega. And then I have this formula here that tells me that if I fix a point, so for every point x0 in omega, and for almost every radius r, such that BR, the ball BR centered x0 is compactly contained in omega, I can write u at x0 as an average, like a spherical average over the boundary of BR centered x0 of the function u. And then this is equivalent to saying essentially the same thing where I replace the average over the boundary of omega with the average, like the solid average, the average over the full ball. Okay, so this, of course, this theorem, so we were going to prove it, but before proving, let me say that this theorem characterizes harmonic functions and tells us a lot about the geometry of harmonic functions, because so this is also, this is telling somehow that the Laplacian is some kind of democratic operator in the sense that if I have a function that is harmonic, so whose Laplacian is equal to 0, then the value of a function at a given point is given by the average over the boundary of this ball. So essentially, harmonic functions don't like high and wide oscillation, so they like to stay somehow close to the point, to the value at a given point, nearby, in a ball nearby. And so this is in essence the starting point of some kind of regularity theory. So that's why we in a sense, it heuristically explains why we have a good regularity theory for the Laplacian. Okay, so let me give a proof of this theorem so that we warm up a bit before moving to the Malmheden theorem. So let me first prove a basic fact, that is that if U satisfies either condition 2 or 3, so if U is equal to a spherical average or a solid average, then U is actually C infinity in omega. And the proof is that this is true because U coincide with a modification of U that I will call U theta. So I will define basically tau theta to be the modifier. So tau theta is a C infinity and compactly supported function such that the integral in U theta of tau theta is equal to 1. And I know that I can write, so U theta will be the convolution of U with my modifier. So U theta is the integral in principle over Rn, but tau theta is supported in B theta. And so this is, sorry, in B eta. And so this is the integral over B eta of tau eta y, U of x minus y. So this is just the definition, convolution of U with the modifier. Okay, and then I can do polar coordinates. So I will call y. I will set y equal to rho omega. Well, now rho lives in between 0 and eta, and omega lives on the boundary of the rho. And so this is going to be a double integral over so the integral in the rho between 0 and theta, and the integral. So this object here for me represents the fact that I'm integrating over a surface. So this is a surface integral. So I know most of the people will write just probably for the sake of simplicity d theta, sorry, d omega. But I like this notation because it reminds me that I'm integrating over an n-1 dimensional object. So it is useful to me even if it's like a complicated notation. Okay, and so u is now u of x minus rho omega, and tau, okay, so tau is a radial, modifier is usually radial, so tau over the boundary of the rho is equal to tau of rho E1. So I just pick one vector, which is rho E1. Okay, and now I use 2, so I know that if I take the integral over the boundary of the rho of u now of x minus rho omega, so this integral here, this is actually the measure of the boundary of the rho multiplied by u of x. Okay, and then I do polar coordinates again, so I take u of x outside, and I do polar coordinates again to tau eta, and I obtain that this is just the integral over b eta of tau eta 1, and this is equal to 1, so this is equal to u of x. So u of x coincides with its modification, which is infinity, so u itself is infinity. And now this proof can be done essentially in the same way if one replaces condition 2, so spherical average condition with condition 3, so solid volume average, because essentially once one knows 3, one can basically reduce the situation to 2 and then do this computation over again. So if 2 or 3, either 2 or 3 is true, then u is infinity. Okay, and now let's do the actual proof. So let's prove that 1 implies 2, then 2 implies 3, and then 3 implies 1. So let me suppose for simplicity that x0 is just the origin. And okay, so I know 1, so I know that u is C2 and harmonic, and I want to prove that u at x0, so u at 0 in this case, is exactly equal to the spherical average. So I will take the derivative in rho of this object. The strategy is that I will prove that this derivative is equal to 0, and then I will check that this is exactly u of 0, that the constant, so this must be constant, and the constant is exactly u of 0. So let's take the derivative. This is a nice computation. So I do a change of variable to move the rho from here to the function u. So this is really just the average integral over the boundary of B1 now of u rho omega. And now I can take the derivative in. So this is the average of the boundary of B1 of the gradient of u at rho omega, scalar product with omega in the Hn-1 omega. Okay, and now I just take the measure of the boundary of omega here out. So the average is just 1 over the measure multiplied by the integral. And here I do I go back to the change of variable. So I do the reverse change of variable that I did here. So I go back to the boundary of the rho, and this is the gradient of u, scalar product with the normal over the boundary of the rho. And then I use the divergence theorem. So this is exactly the integral of the rho of the Laplacian, but then I know that u is harmonic, so this object is equal to 0. So I'm happy because now I've proved that this quantity has to be constant in rho. Okay, and now we recall that, u is continuous C2 in this setting, so by assumption. So I can basically take the limit in rho, where rho goes to 0. And so because this object has to be constant, this integral of BR over any ball BR that is compactly contained in omega this is equal to the limiting rho, and the limiting rho of the average is just U0. So this is exactly the statement in 2. So I've proved that U is equal to its spherical average. So 1 implies 2. Okay, and then 2 implies 3 is really just a matter of some kind of smart use of polar coordinates. Okay, so we want to pass from a spherical average to a volume average. So, I mean, we can imagine it's just a matter of using some kind of polar coordinates in a suitable way. Okay, so I want to write, so for me now x0 is always 0. So I want to write that this object here is equal to U of 0. So what do I do? Okay, so I take out the measure of the ball, and then I use polar coordinates here. So this is the integral from 0 to r of the integral of the now the boundary of B rho of U of x. And now I know that 2 is true, all true. So I can use 2. I can use the spherical average formula. So this is exactly equal to U at 0. Of course, I have to multiply by the measure of the boundary of B rho, because I need to have an average here. Okay, and then, so I can take this out of the, sorry, I make, so I can write that Hn minus 1 of the boundary of B rho is equal to Hn minus 1 of the boundary of B1 multiplied by rho minus 1. This is just the scaling of the Hausdorff measure. And then all this thing can go out. And okay, I can, and of course also the Lebesgue measure of BR is the Lebesgue measure of B1 multiplied by Rn, just by the scaling of the Lebesgue measure. And then this object here can be easily integrated. So this is going to be Rn divided by n. So here Rn gets simplified. And so I have U of 0 here, and then I have this object here, which is the Lebesgue, sorry, the Hausdorff measure of the boundary of B1 divided by the Lebesgue measure of B1 multiplied by n, which is equal to 1, because these two objects, so what is in the numerator and the denominator, they are equal. And again, this can be proved just writing the Lebesgue measure of B1 as the integral over B1 in the x, and then do polar coordinates. And then you will end up with the Hausdorff measure of the boundary of B1 multiplied by some constant, which is 1 over n. So Rn gets simplified, these three things get simplified, and I end up with U of 0. So 2 implies 3 kind of easily once one uses polar coordinates in a suitable way. Okay, and then the last thing is we want to prove that 3 implies 1. Okay, so I know that if 3 or 2, either 3 or 2 holds true, then U is infinity, so U is smooth, so I can do Taylor expansion essentially. Okay, so I'm using 3 here. So this object here, as it is equal to 0, because U of 0 is equal to this average. So I'm just taking U 0 inside the integral here. So this is equal to 0. So this limit is equal to 0. Okay, nice. And now I can use a Taylor expansion. U is smooth, so I can use a Taylor expansion around 0. So this is going to be equal to the gradient of U at 0 x plus 1/2 Hessian of U at 0 x squared plus some order of x cubed, absolute value of x cubed in the x. Okay, and now I can use, and of course I'm taking out the Lebesgue measure of BR here. Okay, so now I can use some odd cancellations, which I wrote here. So because I know, okay, the gradient of U at 0 can go out of the integral, and then here I'm integrating an odd function in a symmetric domain. So this integral is 0. And similar here, if I write this down in coordinates, I will see that this is going to be the second derivative ij of U at 0, and then xi xj. And then if I is different from j, again, I am integrating, for instance, if I integrate in the height direction, I'm integrating an odd function in a symmetric domain, so it is 0. So the only terms that survive, the only term that survive here is the Hessian when I is equal to j. So it's an object of this type. So the sum of second derivative of u at 0, xi now squared. And then this term here, okay, can be more or less estimated and will give me an order of r. If you do like exactly the computation, you can check it. Okay, so here I have something of this type. So I have, so 1/2 is here, the Lebesgue measure of P1 is here, and then I have r to the power n plus 2. And then, of course, this object here can be taken outside. But still, then I have to compute the integral in BR of xi squared. And here I can use not cancellation, but somehow symmetries, because, of course, if I integrate xi squared in BR, it's the same as integrating xj squared in BR. So everything is the same as integrating x1 squared. That can be written explicitly in terms of the integral of modulus, so absolute value, norm of x squared. So I can write explicitly this integral in BR of xi squared. One can really do the computation, but essentially I'm using that. I mean, it doesn't matter which direction I'm integrating, I'm going to get the same value. Okay, and so all in all, I will end up with something. So I will have some r to the power n plus 2, morally, which will cancel this object here. And so I will end up with some constant that can actually be written explicitly. I mean, if we are precise here with the computation, we keep track of the constants, can be written explicitly. Laplacian of u0, and this term will go to 0. Okay, so bottom line is that 0 is equal to some constant multiplied by the Laplacian of u at 0. So u is harmonic. So I've proved that 3 implies 1, and so I've finished with the proof of the mean value theorem. Now, I want you to keep in mind and to remember this proof here, because, I mean, besides the fact that we proved that 0 is equal to the Laplacian of u up to constants in this situation, if we forget for a moment about this 0, we actually proved something else. So we proved that the Laplacian is some kind of expression which is given by the limit of, up to some rescaling here, of the integral, so the average of u of x minus u at 0. So when I will, so of course, this definition is a bit weird, so we wouldn't use this definition to compute the Laplacian of a function. The Laplacian of a function, okay, we take derivatives, we learned in probably at high school how to take derivatives of any function, so easy, and we can use that. But doesn't tell really much about some, I don't know, some kind of properties of the Laplacian, because this is really telling me that the Laplacian is exactly equal to the difference up to this scaling and limit, to the difference between the function u and the average of u in a given ball around this function. So this is really telling me that if this is 0, this is also, I mean, if this is 0, this is also 0, if this is 0, this is also 0. And so, in a sense, the Laplacian is very democratic because it doesn't like high oscillation around that point. So I really want to somehow keep in mind this definition, because when we will define the fractional Laplacian, so the local operator that I will be talking about in the second part, that definition somehow is very similar to this one, put into the context of, okay, fractional operators. So I will recall this one here when we will introduce the fractional Laplacian. Okay, and now, okay, we said that the harmonic functions are somehow characterized by the mean value theorem. But what about the domain? So does the mean value formula actually characterize the domain? So in other words, if I have a function that is, so if every harmonic function in omega, in a given domain, open domain omega, satisfies the mean value formula, can I say something more about omega? So can I say that omega versus is a ball? So does the mean value formula for every harmonic function characterize ball? So there are some results in this direction. So I've mentioned a few here. So the ones by Epstein in 1962, then Epstein and Schiffer in 1965, and then Goldstein and Wellington in 1961. They all prove that this is true up to, so provided that we can add some assumption on omega simply connected or something of this type. And so until 1972, when Cura somehow answered to this question without assuming any further assumption on omega, so omega open. So let me show you the theorem that Cura proved. So if I have, again, an open subset of Rn containing the origin, and with the property that for every harmonic function u in omega, the mean value property formula holds true, then omega is to be one. So the mean value theorem completely characterizes balls. So it can be true in other domains. And I want to give you the proof of the Cura theorem. Well, because it's something that can stay in one slide, really. It's very simple. I think it's a very, very clever proof. So I want to do this with you. Okay, so I am assuming now that for every function that is harmonic in omega, the mean value formula holds true. So u at 0 can be written as the average over omega of ux in dx. And I want to prove that omega is a ball. So we suppose not. So we suppose up to the dilation that B1 is contained in omega, and we also suppose that somehow the bound, so B1 touches omega at some point, so I can find a point y, which is on the boundary of B1, intersecting the boundary of omega, so omega is bigger, and it touches the boundary of B1 at this point. Okay, and then the proof is really based on the construction of, a clever construction of the right harmonic function that works in this situation. So we consider the Poisson kernel here. So this object here is almost the Poisson kernel in the ball. And I'm adding +1, and we will see why. So I will define h of x to be this object here. So x squared minus 1, x minus y to the power n plus 1. Okay. And then, okay, we will not do the computation because, again, it's just really computing the derivative of the function. So one can see that this function is harmonic outside y. And also, okay, h of 0 is 0. This can be easily seen because h of 0 is, so -1 here and then divided by just the norm of y, but y sits on the boundary of B1, so it's norm 1. So we would have -1 plus 1. So h of 0 would be equal to 0. And also the other important thing is that this function is bigger or equal than 1 in Rn minus B1. And this is true because in Rn minus B1, okay, this numerator here is positive. And then I have a +1. So this is bigger or equal than 1. Okay, nice. And now I do my computation and I'm done essentially because, okay, so h of 0 is equal to 0. So here 0 is equal to h of 0. Now h is harmonic in omega, so I can write h of 0 as using the mean value formula. So this is equal to the average over omega of h of x in dx. Okay, now let me take out the 1 divided by the Lebesgue measure of omega. And let me split, because now I know that B is contained in omega, let me split this integral into an integral over B1 plus an integral over omega minus B1. Okay, nice. And now, okay, H is also an harmonic function in B1. B1 is contained in omega. So I can use now the mean value property for the ball here. So the integral over B1 of h of x dx is going to be equal to h of 0 up to multiplying by the measure of B1, because I would have an average here in the formula. Okay, and then I leave the second term, the integral over omega minus b1, as it is here. Okay, now again, h of 0 is equal to 0, so I can forget about this term, and I end up simply with 1 over the Lebesgue measure of omega, integral over omega minus b1 of h of x in dx. And now I use the third property here, that h is bigger than or equal to 0, bigger than or equal to 1 in Rn minus b1, and here I am outside b1, so h is bigger than 1, so this is going to be bigger than the Lebesgue measure of omega minus b1 divided by b1, sorry, the Lebesgue measure of b1. And so, bottom line is that the Lebesgue measure of omega minus b1 is below 0, so it has to be 0, which means essentially that omega has to coincide with the ball b1. So this is the proof that Coulomb gave. And it's, in a sense, it's a simple proof once one understands the right harmonic function to use. Okay, so let me recall, because we somehow used in the previous proof, because we were actually using this object here is essentially the Poisson kernel of the ball. So in a sense, it's not like a random harmonic function that Coulomb was using. I mean, he knew that the Poisson kernel was a nice function written explicitly that could be used. So it's not completely out of the blue. Okay, so this is like how the Poisson kernel of the ball looks like. So you have a nice smooth function which is a pole on the boundary of the ball and then decays polynomially. And the other thing that I want to mention about the Poisson kernel, because this plays a big role in Malmheden Theorem, is that I can write explicitly the solution of a problem of this type. So if I look for an harmonic function, EB1, with the given datum f on the boundary of B1, well, this function has a precise form, which is an integral over the boundary of B1 of the boundary datum f multiplied by the Poisson kernel. So I can use the Poisson kernel to reconstruct an harmonic function in B1 with the given boundary datum. Okay, and now this will play an important role essentially in the proof of the Malmheden Theorem. So Malmheden Theorem, that I mentioned so many times till now, but I haven't said what it is. It's really a geometric argument to construct harmonic functions in a ball given a boundary datum. So essentially, I'm trying to solve this problem, harmonic function in B1, given some boundary datum f. And Malmheden discovered, in a sense, a simple geometric argument to reconstruct the function with simple geometric considerations. So as I said, Schwarz Theorem, which is going to be for us somehow a byproduct of Malmheden Theorem, was proved before in dimension 2, and Schwarz proved this expression that we will see for harmonic function, essentially using complex analysis, which you could do in the plane. So probably Malmheden knew that result and suspected that this was true also in higher dimension, but of course you couldn't use complex analysis, so you had to find another way to do it. And we will see the expression is a little bit different in higher dimension. And we will see also the proof that Malmeron gave and that we presented in all details in the book that I mentioned in the beginning. Okay, so in words, the idea is that one take a point B in the ball, so I have B1, I take a point B, any point in the ball, even also different from the origin, so not necessarily the origin. And then I take a chord passing through P. Okay, so I fix P, and then I take a chord passing through P. We'll see a picture in the next slide, it's going to be easier to understand. And then I take the linear function that interpolates the value of f at the endpoints of the chord. So I have P, I fix a direction, and I take the chord. So this chord will intersect the boundary of V1 in 2 points. I take f of these 2 points, and then I take the linear function that interpolates these 2 values, and I calculate the value of this function at P. Okay, and then finally, okay, I take any possible chord, so I move the direction, and I repeat this argument. So I take the 2 endpoints, f of these 2 endpoints, linear function interpolating these two values, and I calculate it at P. And then I take the average of these values that I get over all possible chords, over all possible directions. And this procedure exactly produces the harmonic function in the ball with datum f on the boundary. Okay, so this is in words. Let's put it into mathematics. Okay, so I take P in V1, and now I fix a direction, E, so a vector E over the boundary, in the boundary, on the boundary of V1, and then I will call Q plus E and Q minus E, and for simplicity I will drop the PE because usually it's going to be clear, which point we are referring to. So this will be the intersection points between the straight line of direction E passing through P and the boundary of V1. That is, one can write explicitly this object. So let me show you the picture here. So this is the picture. So I have the ball, origin is here, I take a point, I fix a direction, and I take this straight line. And then I take these 2 points, so I will call Q plus, the one pointing, let's say, forward, so from P in the direction of E, and then Q minus this one here. And then, you see, Q plus and minus can be written explicitly as P plus some radius in the direction of E, and Q minus is P plus some R minus in the direction of E. Oops, sorry. So Q plus is P plus this R plus in the direction of E, and Q minus is P plus some R minus in the direction of E. So R minus is going to be negative because I'm going backward. And I can write them explicitly. And it's not, they look a bit weird here, but really once one does a bit of trigonometry with triangles there, one can write them explicitly. So Q plus and Q minus are P plus this R plus minus in the direction of E, easy. Now I want to know what R plus and R minus are, and they are exactly minus P, minus the scalar product of P and E, plus or minus the square root of this object here, DE, which is explicit, is P scalar product with T squared minus P squared plus 1. And again, it's not a kind of magic. I can write explicitly, for instance, if I want to write plus, I have to do a bit of trigonometry here. So I have to look at essentially this triangle. And if I take the height of this triangle here, so I see that this object here will be what? The projection of P along E, so this bit here with a minus sign, because P is pointing in this direction. And then I have to add this bit here, which is going to be one side of this triangle, for which I know that this side is 1, this side is 1, and this side here is given by the length of P. So again, I do Pythagoras theorem to get this one here. This is going to be P squared minus scalar product P and E squared. And then I use this information here. So the bottom line is that you will end up with something like this. So if I've not been clear, you can really sit down and do the computation. And it's essentially Pythagoras theorem used twice. But you can write them explicitly, okay? And as you see, R minus is going to be negative here. Yes, because, yes, so DE is positive, and it is also bigger than the scalar product between P and E. So R minus is going to be negative because I'm going in the other direction. Okay. And then, okay, so that was the first point. So fix a point, take the two endpoints and define them in a suitable geometric way. And then I want to take the affine function on this straight line. So P plus R in the direction of E, such that, so I will call LE this affine function. And I want this function to be such that LE of Q minus is F at Q minus, and LE of, one of these two is plus. LE of Q plus is equal to F of Q plus. So there's a typo here. At least one of the two has to be plus, with the plus sign. Okay, so if you, again, do your algebra, you write down your LE of P plus SE. Okay, so S is the parameter moving along this straight line. Again, you do your algebraic manipulations and you write the affine function passing through these 2 points, where now the parameter is S. And so if you do that, if you do your computation, then the affine function is precisely this one here. So it's going to be F Q plus E minus F Q minus E, so this 2 object here, multiplied by S, plus R plus multiplied by F of Q minus R minus F of Q plus, divided by R plus minus R minus. Okay, let me also just notice that R plus minus R minus is exactly this length here. This is the distance between Q plus and Q minus, because this length here is R plus, and this length here is minus R minus. Okay, and then the final step, once I have this function, okay, I have to evaluate LE, so the affine function at P, so I take S equal to 0, so basically I will drop this first term, so I will end up with R plus FQ minus R minus FQ plus divided R plus minus R minus, and then I take the average over E. So U at P is defined to be the average or the boundary P1 of this affine function written here, evaluated at P, in the HN minus 1B. Okay, nice construction. And now what's the point? Well, the point is that if I do like this, then U is exactly the solution of the Dirichlet problem in the ball. So U, as it is written here, solves this problem. So it's harmonic in B1 with boundary datum equal to F on the boundary of B1. Okay, so it is a geometric way of constructing an harmonic function in B1. And to be honest, so I was wondering how Malmheden got to this result, but then I realized, okay, Schwarz did it before in dimension 2. Because, I mean, it's not completely obvious. It's true that the problem is linear. It has some linearity. I mean, it's linear in so many ways, but why does this mean that I have to put a linear function here and then take the average? This is not completely clear to me. And so probably Malmheden knew about the result by Schwarz in dimension 2 and knew the Poisson kernel. So he imagined somehow that there was a simple geometric way of writing the harmonic function. And then the question is why did Schwarz think about something like that? And this I honestly don't know. We will see in dimension 2, I don't know, we will see how the theorem goes in dimension 2, so there's the Schwarz theorem. And maybe we can make some consideration. But okay, so this is our geometric algorithm to produce an harmonic function in B1. Okay. Okay, so an important thing, and the reason why I wanted to mention the mean value theorem at the beginning, is that Malmheden theorem contains the mean value theorem as a special case, if I take P equal to 0. Okay, so here, P is, if you see in the picture, P is any general point, and I'm writing U at P as an average of these affine functions. What happens if I center P here? Well, I know that I have the mean value formula, so I should recover that. And this is exactly the case sorry. So indeed, okay, if P is equal to 0, so let me recall here the definition of our objects. So if P is equal to 0, D of E is 1, so I can't forget about these two. So this is 1. And so R plus and minus, so forget about this, is going to be, they are going to be plus and minus 1. So this is what's written here. And so at the end of the day, Q plus and minus are just plus and minus E, because P is 0 and R plus is 1 and R minus is minus 1. I mean, which we can expect, because if we go back to the picture, if I take the origin, I take the straight line in the direction of E, of course, E lives on the boundary of B1, so this is going to be E1, and this is going to be minus E1. So the notation that we have is consistent with the geometry. And so once we have this, if we want to write a affine function at our point, which is now 0, so I have to write down this object. And if I substitute, so R plus is 1, and Q minus is minus 1, so it's minus E. So is here. And then R minus is minus 1, so I got a plus, and Q plus is E. So I've got FE plus F minus E. And R plus minus R minus, of course, it's 1 minus minus 1, so it's 2. But again, it has to be the diameter of the circumference, so it has to be 2. And so if I plug this into the, if I use Malmheden Theorem, U at 0 is the average of this affine function at 0, which is equal to this sum here. And then, okay, I can keep f of v, and I can isolate f of minus e, so I can split the two integrals, and then I can just make a change of variable. I can send minus e into e, so this will become twice the same integral, so the two will simplify with 1/2, and I will just get the integral of the boundary of v1 of f. And this is exactly the main value theorem. So U at 0 is equal to the average of the boundary of of the boundary of V1 of the value of the function of the boundary. So this is exactly the main value theorem. So Malmheden is some kind of generalization of the main value theorem that allows us to write explicitly in a geometric understandable way the solution of the problem harmonic function in V1 with the given boundary D2. Okay, and now I want to show you the proof of Malmheden theorem, at least one of the proofs of Malmheden theorem. So in the book with Enrico, we essentially recall two proofs. One is the one that I'm going to show you, that is based on some kind of change of variable, okay, change of variable formulas that I'm going to show. And then there is another proof that uses harmonic polynomials. So essentially the idea is that you do the proof for a boundary datum that is given by some harmonic polynomials. In this situation, the geometry gets a bit simpler, so the expressions of all these geometric objects get a bit simpler. And then essentially you pass to the limit in a sense. So you pass to any continuous function. So it's not completely straightforward. It's still a lot of manipulations and algebraic computations. It has the advantage that apparently can be extended also to higher order operators, because you just need to essentially you can write, for instance, a B-harmonic function as a superposition of harmonic functions, and you can use harmonic polynomials. But the proof that I'm going to show you instead relies on this change of variable formula on the sphere, which is this one here, which looks pretty ugly, but it is what it is. So you have a continuous function g from Rn to R. And this change of variable formulas involve all the quantities that we are dealing with this geometric construction. So I can write a simple thing like the integral of the boundary of V1 of this function g as something uglier, which is the integral of the boundary of V1 of g, now evaluated at q plus and minus of omega. So remember, these objects were the two endpoints, so fix the point P, which lives here now. You have the two endpoints, Q plus and minus, given the direction of the omega. So G at these points on the boundary of omega, on the boundary of B1. And then you have, of course, you can write it for Q plus and R plus, or Q minus and R minus. And then here you have R plus minus omega to the power n, and something else here in the denominator. Now, this looks really, really ugly, and the computation did this took some time, I have to say. I will show you like the basic ideas, because once one has this change of variable formulas, so again, I mean, to write this, it's really, you have to do computation once you do the change of variables. So compute the Jacobian of the determinant of the Jacobian of the change of variable that you are doing. But once you have this, you are essentially done, because, okay, suppose for a moment that this change of variable formulas is true. And so if you believe in this change of variable formula, okay, you're done. You can skip, let's say, the proof that I'm going to show you, if you're so confident and you know how to do change of variables. But once I have this, okay, I'm almost done, because now, okay, I know that U of P, okay, so let me say first, essentially the idea is that I have this function that is defined as average of my affine function, which I'm writing here explicitly. And now I want to prove that I can have the Poisson kernel here popping up. Because then I know that an harmonic function, I mean, the function written as average, as integral of the Poisson kernel multiplied by the function f, that's my harmonic function. So if I prove that I can go from here to something involving the Poisson kernel, then I'm done, because U will be my harmonic function written in terms of the Poisson kernel. So in a sense, it's another way, more geometric, if you want, of writing the integral of the Poisson kernel. And probably that's how Malmheden did the proof. So we are going from our proof, from our Malmheden expression, let's say from the expression that Malmheden gave, we are trying to prove that I can get the Poisson kernel. Probably the way he did was the other way around. So starting from the Poisson kernel and going back to something meaningful from the geometric point of view. Okay, so let's do it. Okay, so I write my function explicitly here, and then I split the two functions. So I take R plus f q minus here, and R minus f of q plus here. And then I simply do a change of variable. Basically, I change E into minus E, so Q plus will become Q minus, and Q minus will become Q plus here. So the roles of plus and minus are exchanged here, and I end up with exactly the same thing that I have here. So this is going to be equal to 2, the average integral of just this object. Okay, and then I need to do a bit of algebraic manipulations and see and recognize something in this object. So one can see that this thing here, so 2 R plus divided by R plus minus R minus is equal to this object. Again, this is not, I mean, it's not obvious. So one has to write things down, get the right simplification, and see things in terms of this object here. And then one also has that this is obvious in a sense that this is the distance between P and Q minus. This was R minus with the minus sign, of course, because R minus was negative. And if I recognize this, then I can substitute to 2 R plus divided by R plus minus R minus, I can substitute this object. And to R minus, I can substitute P minus Q minus. Okay, so I end up here if I do the substitution. And okay, now I want to use my nice, or maybe not very nice change of variable. So I want to recognize somewhere the determinant of the Jacobian, so that bit, so essentially this one, sorry, I want to recognize this object here somewhere, and then I will define some G evaluated at Q plus and minus, and I will simplify a lot my life. Okay, so I want to write, so here I've got, you see, I have this object here, which is nice. It's what it is in the change of variable formula. And then I multiply and divide by minus r minus to the power n. And these two objects are the same, again, because p minus q epsilon is exactly r minus. Okay, and then if I call G to be f of e times 1 minus p squared divided by p minus e to the power n, I can recognize that this function here, so this bit here, the first fraction here, is exactly G evaluated at Q minus. So just take Q minus E as here in place of E, and you will get this expression. And now I'm done, because this is exactly what I have in the change of variable formula. So this is equal to G of E. Much simpler now. And now you have to write what G of E is. So G of E is f of E, 1 minus p squared, p minus e to the power n in the end and so on. And this integral is exactly the Poisson kernel of the ball. So this is the Poisson kernel of the ball multiplied by the function, the boundary datum of the problem. And so U, which was given by Malmheden, is exactly the one written in terms of Poisson. So this is the solution of my Dirichlet problem. So this essentially completes the proof of Malmheden up to a minor detail, which is we need to prove the change of variable formula. Okay, so so again, if you feel confident and you know how to do change of variables, you can have a break, or otherwise you can stay with me and we can see how this proof goes. So this proof relies essentially on a couple of observations, which are: the first one is that if I consider this application Q plus and minus, and I take the determinant of the Jacobian, this is equal to this object here. So this is the transformation that I'm going to make. I'm going to make essentially E equal to Q plus or minus of omega. So I want to compute the determinant of the Jacobian of this transformation, and this is equal to what I have in the formula. Okay, nice. And then, of course, the other thing is that I have a spherical change of variable formula, which goes as follows. So if I have a diffeomorphism Q defined on some ring, say B capital R minus BR, that leaves, that doesn't move the boundary of B rho for each rho. Then I have this change of variable formula. So the integral of V1 of G is equal to the integral of the boundary of V1 of G Q omega times the determinant of Q omega. And now, of course, once I have these two, my change of variable formula follows exactly from these two, because once I realize that Q plus minus are diffeomorphism of this type, here I can put Q plus and minus, and then I know this formula here, and then essentially I am done. So I want to prove 3 and 4 now. So I'm breaking up the problem into simpler statement in a sense. So let's prove 4. So let's prove that this spherical change of variable formula was true. And for this, okay, so I start from the integral of the boundary of V1 of G of omega. And, okay, so this stays the same. And then I write, so somehow I multiply and divide by n divided by capital R to the power n minus R to the power n. I multiply and divide by this. And then I realize that R to the power n minus small r to the power n divided by n is essentially the integral of rho to the power n minus 1. This is really a simple computation. Okay, and now I realize, so I keep this constant here as it is, And I realized that this is exactly the version in polar coordinates of this integral here, this integral over this string, b capital R minus b small r, of g of x divided by the norm of x. And now I do my change of variable, the one that I wanted to do. So I call x to be q of y, and q is again my diffeomorphism that leaves the boundary of the rho as it is. So this becomes g of qy divided by the norm of qy in dy. So the ring stays the same, and I gain a determinant here. Okay, and now I do again polar coordinates. So this constant in front is always there. And then I pass to polar coordinates. So this is the integral from small r to capital R of the integral of the boundary of the one of rho to the power n minus 1, g of q rho omega divided by the norm of q rho omega, and then I've got the determinant of this object. And then I'm essentially done, because now I have to choose capital R and little r in a smart way. So I will choose little r to be 1 and capital R to be 1 plus epsilon. And then I take the limit as epsilon. So if I do that, okay, I will end up essentially with, so this object here, if I do a Taylor expansion, 1 plus epsilon to the power n will give me essentially n epsilon. So I've got 1 over epsilon here in front, and then this is an integral from 1 to 1 plus epsilon of something. So this will tend to the value of this function when rho is equal to 1. So I will end up with the integral over the boundary of B1 of g of this object, the determinant of q, which is exactly what I had here in 4. So this is done. This is done. This spherical change of variable is done. So it just remains to check really the most algebraic thing, which is evaluating this determinant. Okay, so we are left with the proof of this determinant, okay? Let me just recall again who these objects are. So again, r plus and minus are written here, and the omega again is explicit, and q plus and minus are given in terms of r plus and minus. Okay, so how do I do it? This is really just careful linear algebra. That took really a lot of time, because apparently Enrico and I are really bad at computing determinant of matrices. And so we did it, we did it over and over and over and over until we got the right result. There are some kind of smart observations that one can do, but essentially it's, okay, I have to compute the determinant of the matrix. Okay, so let's simplify a bit the situation. So up to a rotation, we can suppose that the origin, the point P, and the point P plus omega lie in the plane x1, x2. And also let me suppose, up to rotating everything, that omega is E1, so the unit vector in the direction, in the first coordinate direction, okay? Then, so here I want to use that q plus and minus are essentially, so these are functions that I can extend, that I can define in an homogeneous way. So I will say that q plus and minus at a given point x is equal to the norm of x multiplied by q plus and minus at x divided by the norm of x. So I will extend it in one homogeneous way, this function, to define it everywhere in Rn. And so q plus and minus of omega plus epsilon E1, so omega is E1, so this is q plus and minus of 1 plus epsilon multiplied by E1, and then I use this one homogeneity to take 1 plus epsilon outside. And so this is 1 plus epsilon, and then of course I have just the first two components, because I live in this plane, in the x1, x2 plane, and then all the rest is zero. And now this makes easy to compute the derivative with respect to the first variable of Q plus and minus, because this is going to be, of course, if I subtract Q plus and minus at omega and divide by epsilon, I will end up with Q plus and minus of E1, which is now again a vector with just the first two components different from 0, and then the rest is 0 because I'm living in the plane x1, x2. Okay, so this first derivative is easy, and also we like it because it has a lot of zeros, and when we have to compute the determinant of matrices, it's nice to have a lot of zeros. It simplifies a lot our life. Okay, and then how do I check the derivatives with respect to the other directions? Let's first make this observation. So I have to evaluate now Q plus and minus at omega plus epsilon ej, j different from 1. 1 is already done, easy. Okay, so what is omega plus epsilon ej? Norm. This is omega is equal to E1, so this is a norm of E1 plus epsilon ej. Now, if you write it down, if you write this norm of this vector as a square root of whatever you have, you will realize that this is equal to 1 plus little o of epsilon. So, okay, so you don't have the order epsilon, you have little o of epsilon. So why do I care about this? Because I'm going to use this a lot in the next computation. So Q plus and minus, okay, I'm using first the one homogeneity. So this object is going to be norm of omega plus epsilon ej multiplied by Q plus and minus of this object. But I've just realized that this norm is 1 plus little o of epsilon, which is here. Okay. Okay, and then I have to be brave and go through this computation. So I have to write explicitly Q plus and minus. Q plus and minus was P plus R plus of this object multiplied by the same object. And then allow me to put plus little o of epsilon here, since all the rest does not affect the order. Okay, and now again, I have to be brave again and go through. So this is going to be P remains the same. And then I have to write what is R plus. R plus, if you remember, was minus P multiplied by the vector, which is here, plus or minus the square root of what we called d of the vector. And d of the vector was P multiplied by the vector squared minus P squared plus 1. And then I've got this omega plus epsilon j. And this here again is here. So it's 1 plus little o of epsilon. So it is here. Whatever remains is here. Okay. And then again, I will reuse the nth time that this object here, so the denominator, the norm of omega plus epsilon j is 1 plus little o of epsilon. So, and the little o of epsilon goes here, and same here. I will take common denominator, and then I will see that I will take this outside of the square root and put the little o of epsilon here. Okay, nice. And then let's do this computation. So this is P is always here. So this is going to be P minus P dot omega minus P minus epsilon P dot ej plus or minus, I write down this square root, sorry, this square. So this is P times omega squared plus 2, the double product, so plus 2 epsilon P squared, P dot omega P dot ej minus P squared plus 1. And the rest stays the same. Okay, now I write that omega is E1, so this is going to be 1, this stays the same, this is E1, and again I do another Taylor expansion to take this object outside. So this is going to be 1, 2, and 3, and the term with epsilon is going to be outside with the right geometric object there. Okay, now you see, and again, omega is E1 here, and then I have the little o of epsilon. Now you see I'm not in a bad situation because I can recognize here Q plus or minus of omega, which is E1, so Q plus or minus of E1, which is what? Is this P, and then I have minus P E1, and then I have this plus or minus this thing, so the square root of this thing multiplied by E1. So when I subtract Q plus and minus omega, this thing, 1, 2, and 3 multiplied by E1, they are going to be cancelled, okay? So if I take, so it remains to take the first order in epsilon of this object, okay? So what is this? So this comes from E1 multiplying whatever is multiplied by epsilon here, so P multiplied by EJ, plus or minus this thing here, and this bit is here. So I'll call this coefficient alpha j, it depends on EJ, and after some other algebraic manipulation, one can see that it's written in this form. This is not difficult, it's really just an algebraic manipulation. But it's not over, because I also have the terms coming from epsilon EJ multiplying the terms here, the bounded ones, so the zero order one. So it's this object here and this, sorry, it's just, yeah, I think it's this two. So it's exactly, so it's this one here and this one here, which again is R plus or minus. So I've got R plus or minus EJ. And so just summarizing, taking the first order in epsilon, I can write, and then of course I have to, yeah, I take the first order in epsilon, this object, and then I have the jth derivative, j different from 1 now, is alpha j E1, where alpha j is some coefficient depending on B and EJ, plus R plus of E1 EJ. Okay, so now we are halfway there, because now we don't have the determinant, but we have the matrix. So the matrix, if you remember, was in the first row. So the first derivative was Q plus and minus, and then in first and second spot, and then 0. And then for the rest, it's, you see, it's alpha 2, so alpha 2 till alpha n in E1, and then we got EJ. So in the second column, I'm going to get this, and then in the third column, I'm going to get this in the third row, and so on and so forth. So it's not that bad as a matrix, because, well, it has a lot of zeros, so it will simplify our life. Indeed, if I want now to do the second step, which is the determinant of this matrix, this is going to be what? Well, I take this matrix here, which is an n minus 2 dimensional one, and so R plus or minus of one, so this, the determinant of this one is going to be R plus or minus E1 to the power n minus 2, and then I have the determinant of this little one, the 2 by 2 matrix here. So I have simplified a lot my life, because now this object, I know it, and I have the determinant of a 2 by 2 matrix instead of an n by n matrix, which is always nicer to have. Okay, so it remains to write down this object here, this determinant here. Okay, to do that, so you see, we have to see what these things are and how somehow they play together to give me the right thing. So let's write Q plus or minus. Q plus or minus, where P scalar product with E. Remember, P was living in the plane E1, E2, so it has just the first two components, and then it's 0, 0, 0. And then we have R plus of minus in the direction of E1, where again it was minus P E1 plus or minus the square root of D of E, which was this object. Okay, and then let's sum component by component. So you see in E1, so this is just E1. Here I've got E1 here. So P dot E1 will simplify with this. So we just get plus or minus the square root coming from here. And then and then I can forget about this because it has only one component, the first component. And so I have P dot E2 in the second component, and then 0, 0, 0, 0. And this object here we can recognize is really the plus or minus square root of the E1. Okay, so at the end of the day, the determinant of this object, once I write down Q plus or minus of A1, which is, sorry, Q plus minus 1 is just this bit here, and then Q plus minus 2 is just P2, and then of course I can do the cross product, and I will end up with something like this. Again, it's not immediate. One has to do the product and get and see some simplifications, and then we are almost done, because then one has to do some other algebraic manipulations and see that this denominator here is equal to essentially to what we like. So it's 1 minus p squared minus this thing. Again, this is not straightforward. So one has to sit down, paper and pen, horizontal paper, and write down all the computations. But if one does this, one arrives at this formula here. So I can write what I want in the denominator. And now this is essentially what I want. The last thing that I have to check, so now I know that the determinant is going to be this multiplied by r plus and minus to the n minus 2, which gives me the power n divided by what I want. And so the last bit that one has to check, again, this is some algebraic manipulations. One has to check the positivity, essentially the positivity of the denominator, which is true. So if this is positive, I can remove this absolute value here, and I'm done. So this proves the determinant formula. As you can see, it's not conceptually difficult. Like, I have really to sit down and do the algebraic computations. But one has to be a bit clever and a bit precise in keeping all these terms and doing all the computations right, not missing plus minus signs and things like that. Okay, so this essentially completes the proof of the Malmheden theorem, because this proves the change of variable formula that I wrote in the beginning. And once we have that, we have seen how to get how to prove Malmheden, essentially proving that our formula is nothing but another way of writing the integral of f multiplied by the Poisson kernel in a way that is more geometric and intuitive in a sense. I mean, it's a nice geometric construction. And okay, as I said, now of course, if you have questions, because I don't see the faces, unfortunately, so if you have questions, feel free to jump in and ask, feel free to interrupt me whenever you like. But if there are no questions and we survive this proof with this computation of the determinant of the Jacobian matrix, we can go to the two-dimensional case, which is for which we can say something, because the case n equal to 2 is somehow special. Well, the case n equal to 2 is special in many situations, in this one as well. The situation n equal to 2, as I said, was proved by Schwarz, so some years before Malmheden, and probably Malmheden took inspiration from Schwarz to give his proof. So Schwarz proved this theorem using some kind of complex analysis, as I said. We will see, so we will prove it essentially deriving it from the Malmheden theorem. And so dimension 2 goes like this. So of course the picture is always in dimension 2, but in higher dimension you have to imagine like a solid ball, and you have to do this average over all the possible direction. Here, of course, I have a chord and I'm moving just in the plane. So, and there is a slight change of notation here, in the sense that, again, I take a ball B1 with the origin here, and I will fix a point P. And then Okay, and then I will take a point y here on the boundary. So now I will move around this point y. I will take the straight line connecting P to y and check the other intersection point on the other side of this line with the boundary of B1. And I will call this point Q of y, QP, but essentially I will forget about the P. So this is Q of y. And Q of y is defined, of course, I have 2 points here. So in the plane, I can write explicitly the straight line, so the linear function connecting these 2 points. And then Q of y will be the intersection of this straight line with the boundary of B1. So if I do this thing, this algebra, well, I will end up with a precise definition of Qy. So Qy is going to be y minus something p minus y. And I can check that this object is exactly, so it has norm 1, so it is on the boundary of B1. And it is given by this intersection. So it's very similar to what happens in Malmheden. Just here, I'm not fixing exactly, well, in a sense, I'm not fixing exactly a direction here. I'm fixing a point, moving around the point, and I'm taking the other intersection point on the other side. So Q plus and minus are somehow replaced by y and Q of y. And the Schwarz theorem tells us that in mention 2, if I write U of P at any point P in the ball as the average over the boundary of B1 of f of this Q of y, then this function is the solution of the Dirichlet problem in the ball. So Laplacian of U equal to 0 in B1, U equal to f on the boundary of B1. Okay, so yes, so it's slightly different from Malmheden in the sense that in Malmheden I was writing here I was writing the average over all possible direction of the affine function evaluated at P. Here I'm writing f evaluated at this point here. So it is slightly different. And okay, so if you think about in dimension 1, Malmheden theorem and Schwarz theorem are kind of obvious because because harmonic functions in dimension 1 are straight lines, and so they are completely classified. They are just straight lines, and the boundary of B1 is just 2 points. So essentially, with Malmheden and Schwarz, I'm writing just a affine function connecting these 2 points, which is harmonic because we know that straight lines are harmonic in dimension 1. So if you think about in dimension 1, both Schwarz and Malmheden are not really saying anything. I mean, Malmheden is trivially true. It is not giving us any other intuition, any other information. While in higher dimension, this idea that you can somehow use this affine function interpolating the 2 endpoints, it kind of say something. I mean, it's not zero information like in the case of dimension 1. Okay, so before showing how to prove Schwarz theorem, there's a nice application of the Schwarz theorem, which is in a sense a physical application, if you want. So suppose that you are in dimension 2, so you have a disk in dimension 2, you have a plate, and suppose that you know the temperature along the boundary. So suppose, for instance, that this temperature is equal to 1 along a given arc of the circumference of the disk, and then it's 0 along the remaining bit of the boundary. Okay, and so the question is, okay, I have this plate, temperature given on the boundary, so 1 along an arc, 0 along the rest. Can you tell me the temperature at a point P of the disk only using elementary geometry, so without knowing, any physics, diffusion, and things like that? So I want to tell you what the temperature at a given point inside the disk is, given that I know this boundary. And now I can pretty easily with Schwarz, because, for instance, okay, so this is the picture, okay? So I have the disk in dimension 2, and suppose that the temperature is equal to 1 along this arc, along this arc sigma, and then is equal to 0. So my function on the boundary is the characteristic function of sigma. Okay, now remember Schwarz. Schwarz tells me that U of P is the average of over the boundary of F evaluated at essentially the Q of omega. So in this situation, F is the characteristic function of sigma, and I have to evaluate it at Q of omega given omega in sigma. So what is Q of omega given omega in sigma? Well, I have to consider P, and I have to take, you see, I have to consider the endpoints and take the projection passing through P to the other side, same here. And so the Q of sigma is going to be exactly this arc, sigma prime. So this is given by the projection of this arc, sigma, across, so through sigma, through P to the point P, to the other side of the circle. So at the end of the day, okay, so this is what I was trying to say. So one projects the arc sigma through my focal point at which I want to compute my function U. And I obtain a conjugated arc, sigma prime. Okay, and then the temperature at P, so U at P, is exactly equal to what? Well, okay, so this is the average over the boundary of P1 of F, and now F is the characteristic function of sigma evaluated at Q of omega. So it is exactly the length of sigma prime, right? Because it is the characteristic function of this thing. So it is exactly the integral at the end of the day over sigma prime. So it is the length of sigma prime. And then I have to take the average, so I have to divide by 2 pi. So this is exactly the content of the Schwarz theorem when F is equal to the characteristic function of sigma. So I can easily answer to this question. So given the temperature of the boundary, can I say the temperature of my plate at a given point P using Schwarz theorem? The answer is easy. UP is equal, in the specific case of temperature 1 and 0, is equal to the length of the conjugated arc sigma prime with respect to sigma, with respect to P, so sigma with respect to P, divided by 2 pi. Done. So I don't have to do I don't have to solve anything else. Easy. So it's in a sense an easy geometric way of writing down the harmonic function that solves my problem. And it has a nice application, for instance, if I want to say that, if I want to tell the temperature of the boundary of a disk. And I don't know if the reason why Schwarz looked into this problem, because these people at that time were everything. They were mathematicians, they were physicists, they were engineers, so they were really, really good. So today we are really picky with how people define ourselves. So we are analysts, we are pure mathematicians, we are this and that, and we are very picky when people tell us, oh, you are applied, this is applied mathematics, pure mathematics, and things like this. But these people essentially were just really good. So probably the reason why Schwarz were looking into this probably came from some specific problem of this type, and we ended up with a nice mathematical formulation of a problem of this sort, which has a nice application in terms of giving me a temperature of a disk given the temperature on the boundary. So you apply the Schwarz and you get it straight away. Okay, so, okay. So this is important because so Schwarz is slightly different from Malmheden. Malmheden here had, as I said, had the affine function. So the average of the affine function rotating, so moving around with this direction. Here you have exactly f at a given point, a given endpoint, moving the other endpoint, essentially. So it is slightly different. It is a consequence of Malmheden, we'll see, but it is slightly different. And okay, one can ask, can one prove the Schwarz theorem also in higher dimension? So why is Malmheden theorem different? Why had Malmheden something different there? Why is Malmheden averaging something different and not exactly Schwarz theorem? Well, it couldn't. I don't know if it tried, but it couldn't, because the Schwarz theorem only holds in the plane. So it's not true in higher dimension. Why? Okay, let's cook up a counterexample. Let's see. Suppose that the dimension is bigger or equal than 3. And let me take sigma now, the lower half sphere. So it is the boundary of V1 intersected with xn below 0. Okay, so it's the lower half sphere. So I'm just taking the lower half sphere, like we are doing in this mini course. And then let me take f, so as a boundary data with a characteristic function of sigma. Okay, and then suppose that Schwarz theorem holds true in higher dimension. Then the function of P given by the surface area of the spherical cap obtained by projecting sigma through the point P, like we did before, would be harmonic. But this cannot be true. And the reason is the following. Okay, so I have my half, okay, it's a two-dimensional picture, but we have to imagine that we are in n dimensions. So there is some directions x prime, so from x2 to xn minus 1, exiting the screen. And then you have x1, xn. So if epsilon, I fix epsilon between 0 and 1, and I take p, so my function is characteristic function of this bit here, below, xn below 0, and I take a point P to be this one here, so 0, 0, 0, 0, 1 minus epsilon in the hand direction. So it's a bit, it's here very close to En, essentially, but it's like epsilon far from En. Okay, and then one can do a bit of trigonometry, and one can check the order of UP. So UP, if Schwarz were true, so I have to take f of q of omega. Now f is the characteristic function of sigma, and sigma is this bit below. So I have to take the conjugated arc through P. So this is my endpoint here, and this is going to be my endpoint here. And so all this half sphere here is projected in here. And this bit, so at the end of the day, UP is going to be this length here, or better, this area, because we are in higher dimension. And then one can do a bit of trigonometry. And this is not completely clear. I don't know if you can see it by some kind of dimensional analysis, but if you do a bit of trigonometry, you can check that U of P is of order epsilon to the n minus 1. So in dimension 2, that would be order epsilon. Otherwise, we have epsilon to the n minus 1. Therefore, if I try to compute the normal derivative of U at this point, 0, 0, 0, 1, so En, this has to be the limit when epsilon goes to 0 of U evaluated at P, so slightly below, so the normal is pointing in the n direction, okay, so I'm going in this direction, minus U at 0, 0, 0, 1, and then divided by epsilon. Now, U at 0, 0, 0, 1 is 0, because my function f, U on the boundary coincides with f, and f is 1 just here, and then 0 on the upper part. So this is 0, and this is order epsilon to the n minus 1. If n is bigger or equal than 3, this is going to be epsilon to n minus 2, which is going to go to 0 if n is bigger or equal than 3. And this is against Hopf lemma. Hopf lemma tells me that the normal derivative has to have a sign, can't be 0. And so Schwarz theorem cannot be true in higher dimension. Notice that this is not a counterexample in dimension 2, because in dimension 2 this would be epsilon. So I would have, again, this would be 0. Here I would have epsilon, and then I would, or let's say a constant times epsilon, and so this would be a constant different from 0. So this wouldn't give me a contradiction with Hopf lemma. So Schwarz theorem cannot be true in its form in higher dimensions. So Malmheden had somehow to find another expression. And of course, if you believe that the way of doing is probably to start with Poisson and doing essentially the computation that we did, but going backward. So starting from Poisson, going backward and trying to recover something meaningful from the geometric point of view. That's probably what he did. And okay, so I think I'll just present you these slides. So I'll give you the proof of Schwarz theorem. So not in the way that Schwarz proved it, but in the way that we proved it in the book, which is essentially deriving it from Malmheden. And then I'll probably stop here and maybe take questions because I've spoken for a lot of time. Okay, so I want to prove Schwarz using Malmheden. So let's notice this. If I take Q plus, Q of Q plus is going to be Q minus, because if you remember the picture, I had Q plus here, Q minus here, and in the notation of Schwarz, Y and Q. So if I take Q of Q plus, this was Q minus, and if I take Q of Q minus, it was Q plus. So the action of Q on the point Q plus minus is nothing but reversing the sign. So Q of Q plus is Q minus, Q of Q minus is Q plus. Okay, and then we have always to use, we have to remember the change of variable formula. So I have to, okay, I want to prove essentially that my function u as it is, so as it is defined by Schwarz, is nothing but the function defined by Malmheden at dimension 2. So I'm going backward to reconstruct Malmheden essentially. Okay, so I start with Schwarz. So this is the integral of the boundary of V1 of f of q. And let me call now g. Now my function g is going to be f of q. So this is the integral of g. And now I use my change of variable formula. My change of variable formula with q minus. So this is g of q minus times the determinant. The determinant had this structure. Okay. And now I write again f. So I write again what g is. So g is f of q of something. So f of q minus, and I leave this as it is. And q of q minus is q plus. So this is f of q plus multiplied by this object here. And then again, one has to do a bit of algebraic manipulations to see that this bit here, and probably this comes from some of the identities that I wrote to prove Malmheden. So these two bits are the same, and then again, this, I think these two are plus or minus divided by u minus p squared is 1, and so one end up essentially with 2 r minus divided by r plus minus r minus. And if you go back, of course, now you have to you have a 2 here, so you have to split the integrals into 2 terms and do one change of variable into one of the two to recognize. So here you have f of q plus r minus. In the other one, you have to recognize f of q minus r plus. But at the end of the day, you end up with the harmonic function constructed by Malmheden theorem. Yes, so I think I will stop here for today, and yeah, I will take any question. Thanks for listening. Thanks for your patience following all these algebraic computations.